Be a little long term at the end of the day. All right.
All right.
Are we ready?
Yeah.
Let's go.
He goes first and then I go.
Okay.
I'm going to start this so we can have the maximum time for the next. All right, welcome everyone to the EECS Colloquium. Thank you for being here. My name is Eric Paulus. I'm just going to give a very brief pointer to next week. We will have Rodney Brooks here as a speaker. But I want to give our time, you heard it here, Moore's Law is not dead. So today we have a really special introduction by our very own Dean Sujay King Liu.
Thanks very much, Eric. Good afternoon, everyone. So I'm Sujay and Dean of the College of Engineering, but I'm a professor of electrical engineering and computer sciences. And it's my pleasure to introduce Jim Keller. He's a senior VP and general manager for Silicon Engineering of the Silicon Engineering Group at Intel Corporation. So you might know that Moore's Law refers to Gordon Moore, who's an alumnus of Berkeley. And Moore's Law really has set the pace for exponential advancement in computing performance over the last 50 plus years. And there has been a debate for many years about Moore's Law being dead. And Jim will call out some people who have said that on the record. But in any case, Jim is really well qualified. Let me tell you, so Intel Corporation was co-founded by Gordon Moore. So this is really, he has we would hope that Intel would continue to be the company that ensures that Moore's Law is not dead. But Jim has impressive background. Before coming to Intel, he actually had more than 20 years of experience designing microchips, computer processing units, not only with the Intel's x86 architecture, but also the ARM architecture, which is derived from the reduced instruction set computing architecture developed here at Berkeley. And so he designed these chips, or he led the development of these chips for many applications, so not only servers, but PCs and mobile devices. And before Intel, he was actually at Tesla. He basically helped them design their chip for automated driving. And then before that, he was actually at AMD. You might have heard of AMD's recent successes with the Zen architecture, the CPUs. That was Jim, okay, that led that chip development effort. And before that, he was at Apple, which was through a company acquisition. There he led the design of the A4 processor, which powered the iPhone 4, and subsequent Apple 5 processor. So really impressive experience, great perspective to share with us today. He did get his bachelor's degree in electrical engineering a few years ago from Pennsylvania State University. So without further ado, please join me in welcoming Jim to Berkeley EECS.
All right. And is this on? Great. Well, first, it's almost 40 years. It'll be 40 years of computer design next summer, which is starting to make me feel old. But I'm an architect. I have a title that says SVP, and I really wanted that because of the big S. I was going to put that on my shirt. Like, I don't mostly think, well, my staff knows better. I'm not really a manager, but I have a really good staff, so we run a big organization. And Silicon Engineering at Intel is like 10,000 people. So it's a wild phenomena, and I'm delighted to be there. It's super fun. But when I joined, everybody's saying Moore's Law is dead, and since Intel's the Moore's Law company, I thought, well, it's kind of a bad career move. Like, what am I doing there? But I also been thinking, people have been telling me Moore's Law is dead in 10 to 15 years for my entire career, and I realized about 10 years ago I stopped worrying about it because despite its imminent demise, it kept proceeding. And so at some level, I don't care that much, but then I had this funny problem because, let me just walk you through a little 2x2 matrix. Everybody knows how they work, right? So 2-axis, Moore's Law is not dead, or it's dead, and then you believe in Moore's Law, or you don't believe in it. All right, here's a matrix, and I'm going to walk you through the matrix a little bit, and then I'll tell you about why I think it's important. So if it's not dead and you believe in it, well, it's challenging because you got twice as many transistors every couple of years, and your designs get bigger and harder, but you're sort of ready, right? And if it's dead and you think it is, you're a little delusional, right? And many people think that's how the world works, and that's fun. And then if it is dead, and you don't believe in Moore's law, well, it's going to be sad, because if you're in a high-tech computer company where things aren't really changing, it's going to be a race to the bottom, and that's a different thing. Here's my problem. If it's alive and you think it's dead, your design teams, your methodologies, your architects aren't getting ready for the next wave of more transistors, right? And that's a tough situation. And at Intel, we had some groups that literally the design team doubled when we got twice as many transistors because they had twice as much to do and the tools didn't scale. And so and I don't want to be pedantic about the details of Moore's law, because my fundamental challenge is the scaling, right? So, and I really want to say, because of the endless change in transistor count, it's enabled a whole bunch of changes. People say computer design is X, but it's changed so much over the last 40 years that I've been doing it. And it continues to change, and we're reinventing new CAD tools. So not only is the transistor roadmap continuing, but adjacently memory, packaging, many, many things. And that's causing us to rethink architectures and how we do things. So I want to walk through this a little bit. So, and one interesting thing, and again, I'm intrigued about the phenomena of how things scale. So if you sort of glance down here, you know, transistor per core has gone up 1,000x, frequency 1,000. I'll get back to some of the details later. Wafer size hasn't changed that much. Transistors on a chip, it's way up. Cost per transistor, 10 million. So the operating voltages, 5 to 10x depends on where you started. So, things have scaled very irregularly, right? And depends on which technology part you're looking at. It's a very uneven thing, but the net has been very strong scaling. So, and everybody's seen all these. It's kind of fun. Moore's law is dead, now what? But I like the other one. So this happens all the time. Everything that can be invented has been invented 1899, right? All right, there's a deep intellectual framework about how things scale and move along, right? And it's easy to be attached to a set of technologies and then think that's kind of the limit. And the declaration of the end has happened multiple times. Now, when I worked at Apple, I had 2 vendors come to us to talk about CPU performance. And one said, CPU performance per clock is kind of plateaued. And the future is parallel programming and accelerators. Intel showed up and said, we're going to make 5 or 10% year CAGRs. Compound annual growth, 5 to 10% a year, which sounds a lot better than plateauing, right? And our internal plan was to do a new core that was twice as fast, and then do one after that was twice as fast. And if you look at the Apple roadmap, that happened, right? The expectation and mindset sets your direction and your possibilities, and it's important. So here's some famous skeptics. and my understanding is they're both very smart people. And I've talked to Dave, and I can validate that. Jensen is kind of interesting. I never quite got that. His whole business is bigger, faster GPUs. And why he's running around saying Moore's law is dead, I don't know. But somebody told me that one year they announced 12 nanometer and AMD was going to announce 7. He wanted everybody to think the technology didn't matter. I don't know if that's true, but it's a fine story. But that's sort of puzzling. So, and then the funnier version of this is, so there's a little of a cultural idea about this, right? And again, my problem is if I'm getting twice as many transistors, and sometimes we say transistor, sometimes we say transistor times frequency, there's a whole bunch of things that drive it. What, as computer architects, designer, tool makers, fabricators, are we going to do, right? So we've been digging into understanding this, and it was interesting how many different things we popped up. So everybody's familiar with this curve, right? Diminishing return curve says you have a technology, you do an invention, and at first it accelerates pretty fast, and then you reach the limits of it. So think rotary phones, super exciting, right? And at some point you had the best rotary phone you can do, and then push buttons came along. That was super exciting. You know, the buttons got better and better, and then touchpad. You know, it's a cascade of these things. And if you go look at S-curves of the computing stack, they're sort of everywhere you look. We wrote assembly, hit the limits of that. We wrote C. I worked at Digital Equipment when the VMS operating system was written in assembly, right? And everybody's moving to C, and they thought, well, we'll just make a better assembly. They called it BLIS, which is essentially assembly with a compiler on it, right? And they keep moving along. Processor architecture, single thread, there are plateau reasons for there. We went to multi-thread, to GPUs, and now we're building computers that know how to parse through petabytes of data and do computationally highly effectively. So we keep changing the game as we go through it. So what did Gordon say? I really like this. First time I read it, I thought it was really funny. Cost of transistors is falling, the number of components per circuit rises by 75. We'll get as many as 65,000 components on a chip. And I thought he's only off by a factor of 1 million, because we're at 65 billion transistors a chip. We now measure transistors in 100 million transistors per square millimeter. But of course, he was the founder, and he did say in 75, right? So this is a pretty simple roll, which is fun. And Moore's law famously drove what's called Bell's law, right? Mainframe, mini, workstation, PC, laptop, a faster, smaller version of the same computer every 10 years or so as we shrunk it down, right? And there's all kinds of incredible things in the history of this. IBM built an out-of-order machine out of essentially tubes, right? Discrete transistors years ago, right? And this transformation kind of hit the limit on smartphones, and I'll return to this point at the end, right? There's a lot of arguments about Moore's law, right? One is, well, there's a limit to optical scaling, there's a limit to the cost, right? And what we keep finding is, as we drive it into mass production, we always solve for cost. We've always solved for power. We've always solved for whatever limiter is in the way. And then Kurzweil, I really like this graph. He went and plotted, and I don't know if this is exactly true, but it's super fun. He said, computing technology has been on this, log linear curve since 1800s, right? It didn't just start, and there's been many transitions of what you build a computer at, but that's continued to generate this exponential growth in computing power, right? Which is a really fun slide. All right. So, on the one hand, individual technologies tend to be on diminishing return curves, but total computing power is on an accelerating return curve, right? Build faster computers, you get more technology ideas, you have tools to analyze stuff, you have compound growth, and it keeps going. So what's going on under the sheets, and many people have observed this, is accelerated return curves are typically made out of a cascade of diminishing return curves, often of very different kinds of things. Rotary phone, touch phone, or keypad touch phone. Like what drives the next wave of innovation often is a very different thing, right? And then here's the human nature problem, which is when we really understand something really well and you're hyper aware of what's going into the innovation curve and you're standing on it, it's really easy to see that as plateauing. But in fact, what we've seen over and over and over, the next innovation curve moves us along. Does that make sense? So some of Intel's own scientists, Paul Packham got quoted, this is pretty funny, he got interviewed by the Wall Street Journal and said, we're not really sure we can drive technology much further. And the next day was a press conference with Oda Laney, the then CEO of Intel. And they said, so Intel engineers think Moore's law is dead. And he said, I talked to Gordon this morning. And he's still doing fine. And then he turned around and said, who the hell's Paul Packham? Interestingly enough, Intel is a very tolerant company. He's driving our 7-nanometer transistor definition. and Ruth, appropriately named Ruth Brain, she's super smart. the factors that go into driving transistor shrink are complicated, and there's many, many technologies. And it's easy to point your finger at one or more of them and say, I see the limits. But the details about how we drive this forward and the trade-offs we make are really, really quite interesting. So, you know, when I first started hearing about Moore's Law, it was about optical scaling. We had 2D transistors, and we slowly made them smaller, right? Then we changed materials, low-K dielectrics. We changed the transistor architecture, right? The scaling things underneath that. Does everybody remember when the big problem of semiconductors, actually looking around, maybe nobody does. We put one metal layer down, and then another one had to go over it. And then the next one went over it, and the bump got higher and higher. And all the technology development is like, how do you keep the metal from thinning as you got the higher metal stacks? And somebody figured out how to grow oxide on it and sand it flat. They called it planarized metal, but it was sandpaper, right? Transform, now when you look at a metal stack, you see these beautiful flat metal layers with vias. There is so much technology in that stack. There's different metal technologies. The sandpaper got better, right? So the hunt, like literally, it's very smooth. It's super fun. All right, so we're looking through the laws of this stuff. So I worked at Tesla for a couple of years and got to know Elon a little bit. And one of the things Elon is fantastic at is, what does he really want to build? And he used to say, you first figure out the configuration of atoms. Then you figure out how to put them there, right? Now, he meant that in terms of rocket ships, car factories, lithium batteries, right? He started building electric cars confident in this model, that when you look at the fundamental physics of lithium-ion batteries, it has a cost trajectory to get there. And everybody said, well, lithium is expensive. No, it's not. It's a common metal in the earth. It was expensive because the lithium mines had been sized for, get this, lithium grease for industrial applications. It was a capital problem. It's $1 billion to build a lithium mine. But once you build them, lithium is relatively cheap. It's very low technology extraction, right? So the summary I tell the engineers now is, don't let the hows constrain the whats, right? When you want to build something, sometimes iterating on the current set of hows is important. Sometimes it's completely different. I want to say something about power scaling. So I hear often, power scaling is the limit. So back in the late 90s, I was at Digital working on alpha computers, and we're building a supercomputer with Cray. And their line was a megawatt per teraflop. Right? And they said, we really need to improve this by 10 to 100x, and we're working on it. But a megawatt, you know, get 100x out of that, that's a hard number, right? We just crossed a watt per teraflop, a millionx improvement in power in 20 years, right? And then I think it's almost ironic that as power scaling went down, we're starting to hit the thermal limits of power flux density through a square centimeter of silicon just at the time we can really stack it properly. That's one of the ironies. But we're using stacking for a whole bunch of things, currently memory, and we're starting to look at logic architectures where we stack it, and even though the peak power flux through the vertical is too high, there's a whole bunch of tricks to manage that power and do something about it. So I'm personally confident that we're going to keep moving the power wall, and the number of changes that we've already done is high, and we're not done yet. So let's just talk about the current, you know, thought process on where we are. So we had planar transistors, we went to FinFET, where we're all building nanowires in the fab, right? Intel, TSMC has announced. I don't know if they have. Samsung, everybody's working on it, right? And there's a really interesting thing, while the world thinks Moore's Law is dead, all the fab and the technologists think it's not, and everybody's announced now a 10-year roadmap for Moore's Law. And if you actually looked at it, from the left side to the right side here is about 5,000 times shrink, right? Actually, if we scaled this properly, you wouldn't be able to see it, so we just scaled a little bit. And then what's driving this stuff? So here's a fun slide. We're staring at this go, when we plotted the wavelengths of light, so when I first heard about this, the wave, as they got smaller, the wavelength got too small and they started interfering with it. But if you actually look at the wavelength stacking, we went from 436 to 193, while the feature scaling was actually exponential, right? Which is pretty wild. Then EUV shows up and that really resets the wavelength, right? So we get back to direct printing. And with EUV, we were talking earlier today, it should have been, introduced way back here before we had to go crazy. But look what they actually did. So here's a different way to graph it. So the wavelength on the vertical thing generated the printed dimension on the bottom, right? And this is a super fun thing. So when the wavelength first got small, it started to interfere, so they started tweaking the pattern. They tweaked the wavelength, they tweaked the material it went through, and then they started doing, computational lithography. So they started in 1990 with printing with no correction, and then they started doing minor correction, and then basically they started printing on the mask the field that you wanted so that when the light interfered a little bit, you got what you wanted, okay? And then things started to go crazy. That's the pattern you print on a mask to print an X, right? And they got something like 20 to 50X out of that. And then here's a set of patterns. And you're probably looking at it goes, what is that going to print? That, right? So the limitation of wavelengths that everybody thought they understood was, and at some level you can think, well, the semiconductor business is complicated. There's physicists and chemists and material people and machine people, optic people, the diversity of technologies driving this is so high. And now we're even using AI, so we evaluate how we build stuff. We have big data sets about what works and what doesn't, and they're starting to do closed loop of what do we build, what do we print, what causes defects, and then what do we do about it. Super interesting phenomena. So I'm going to whip through a path to 50x. So I talked to a bunch of engineers in Intel, and I said, I really want a path to 100x scaling. This is 100 times more transistors per square millimeter. And after about 3 weeks, they came back in a room full of people, and they said, they looked kind of glum because they only got to 50 in 3 weeks. And I asked them to maybe spend a couple more weeks on it. And we're still looking at it, but this is the first graph. So there's fins, right? And we have clear line of sight to pitch scaling the fins. This is printing fins, and there's a whole bunch of metallurgy. Now I want to point out that the top of the fins is still over 100 atoms wide, right? So we're not running out of atoms. We know how to print single layers of atoms. There's a whole bunch of process steps where the metallurgy is really interesting in terms of small number of atoms, but the fins themselves, they're mountains, right, in terms of atomic layers. Right, we're going to nanowire stack, and the way we build the nanowires, we get more drive current, because with gate all around, you get way more control of the device, especially at low voltage. We're super excited about this. It's another factor of 2. And then we're going to go stack the nanowires. So in the same nanowire stack, we'll get P and N devices. Then we already do wafer-to-wafer bonding. And I'm not going to go into all the details of this, but we're starting to build stacks of transistors and metal stacks to, there's the goodness both in how the metal stack drives down to the transistors, multi-sides, and there's goodness about how we build logic functions. 3D stacking is going to be more and more important as we build stuff. And just think about a big building. If you want lots of square foot and it's one layer, the distance is the XY from anywhere. If it's stacked, the distance is XYZ, it's way shorter, right? And then finally, we already do die-to-wafer stacking, and it's not clear how high we can do that. Now, people have said, well, that's more wafer steps and more processing and more costs. I've been talking to fabs for like 30 years now, and they always promise me at some point in the near future that wafers are going to be too expensive and the cost per transistor is not going to cross over, and it's never ever happened. It's unbelievable how fast that happens. If we go in the high volume manufacturer and you work on it, and we've just seen some remarkable things. When TSMC announced the 16FF process, it was fairly complicated. They got the FFC, they radically reduced the number of wafers. Right? You can put a wafer through Samsung 14, and I probably shouldn't quote the number of days, but it would shock you how simple it is. Right? So we always figure out how to do the what, and then we always radically improve the how. Here's a funny one. Wire bond technology way back in the 80s and 90s was the limit because of inductance in these wires. And then the wire bond guys and the flash guys got together and they shipped production products where a wire bonder went 1, 2, 3, 4, 5, 6, 7, 8. This is 8. They got up to 16 in production. Right? So the flash cells were getting smaller. To get more flash in the package, they stacked them. And it got too complicated, so they decided to stack layers of flash cells vertically. And I found this picture and I thought it was really funny because that's actually the Babbage difference engine from 1854, right? That was a meter. Modern devices are a nanometer. 10 to the 9th shrink. And here's a modern flash device, which looks a whole lot like a Babbage engine, which cracks me up. They're now up to 128 layers thick. Now, those are very simple layers. Now, just imagine that those layers get a little more complicated and we start building 3D devices really deep, right? So the limits of shrinking, you know, I sometimes feel we're so far away. Like, I'm not sure how many atoms across we need. Things are sort of quantum mechanical or 2 or 3. We know how to print single layers of atoms. We know how to, we're going to know how to print down to small numbers of atoms, and this is going to keep going. Okay. Back to how this changes computer designs. Now, the really interesting thing is, like, I'm an architect, right? And if you go look at the frequency moved by 1,000 and the transistors per core moved by 1,000, the cost moved by transistors per millimeter by 100,000, the bottom two numbers are kind of sad because memory latency as seen by the processor went up 100x, right? You know, at 4 gigahertz in 100 nanoseconds, that's a lot of cycles. And the instructions per cycle, while it's improved a lot, isn't nearly like the rest of the curves, right? And does that make sense? So if I go sit down with my partners, you know, the frequency guys, the transistor density guys, and the microarchitects, I'm the low man on the totem pole, right? And a lot of times we look at graphs like this and think, and this is a famous graph which I quite like, that the performance ramped linearly for a while with frequency and process scaling. And it's been tougher to ramp that as the frequency didn't ramp, but we had lots more transistors. Now, we are continuing to move this along, and my personal belief is some of the limits of this have been mindset about how far can single-threaded programming go, because we're actually going to do something about it, but there's a whole bunch of dimensions on this. The programming guys kind of cracked me up because here's an old C program that did something interesting, convol 3x3, and then in OpenCL it looks about the same. We wrote a PyTorch program that looks, you know, like one-line call, right? And I just want to talk about abstraction layers because this graph right here is super interesting. Somebody said, you know, when we went from assembly, you write a line, you get a line. You write C, you know, it's something like 10 lines of executed code for every line. You go to a C++, it goes up, and depends on who you are, what programs you look at, you get a graph, something like this. And there's 2 arguments about this. One is, boy, modern programmers are inefficient, right? And if you're using JavaScript to write hello world, it's probably true. But you can write 1 line of code today and fire up a data center and find a cat photo. And if you tried to do that in assembly, you'd have 1,000 people working for 1,000 years and they'd fail, right? So the interesting thing about the abstraction layers, and this goes for computing in general, the reason processor performance is sublinear with transistor count is because it's limited by unpredictability, branch predictability, data predictability, sometimes instruction predictability, right? But we are building the new abstraction layers to meet that need. In some places, it's linear. We added a lot of floating point extensions, bigger floating point, and that can be linear with processing. And then the AI stuff has been super linear with processing because the architectural innovation that was allowed by the huge increase in transistors came along. All right. I gave a talk on microarchitecture recently, and I just wanted to, the innovation track on microarchitecture has been hilarious. The computers used to be pretty dumb. Fetch, execute, write back, right? Super small, super short. And then the risk innovation, I think, really started is like, let's stretch out that pipeline, do the minimum amount of work on each stage. It was super, super exciting. And then many went, super scalar, and then they went super scalar, super pipeline, and then they started to build big out-of-order machines, or big super scalar, super pipeline machines, right? And we saw sequential improvements in performance. And then one of my favorite computers, because I was the architect of this, was EV6. It was digital's first big out-of-order machine. So we built fetch 4 instructions. We had 2 full integer, 3 integer, 4, it's not quite drawn right, 3 integer pipes, 3 floating point pipes, big execution monster. We had a whopping 24 instruction window in the scheduler and 100 instructions in flight, right? Here's a, let's say, abstracted diagram of a recent Sunny Cove. So the 800 instruction window sustains between 3 and 6 x86 instructions a clock. Massive data predictors, massive branch predictors, right? And if you look inside it carefully, it's not one big computer anymore. There's a fetch predictor, a branch predictor, an instruction fetcher, a micro op engine where we take decoded instructions and execute them. Every single piece of that computer looks more complicated than a computer. Now, going from 0.3 IPC to, let's say 3 or 4 IPC is only 10x, but the memory latency went from 1 clock of memory back in the good old days to hundreds of clocks of memory latency. And when you're running floating point code where we can really apply that acceleration, it's completely different. Now, one thing, I was talking to some software people, and one guy was looking at it and he said, "You're scaring me, the complexity of this engine. Like, how do you ever verify it?" There's been recent people talking about, well, you have 1 million flip-flops in a computer. In principle, it has 2 of the million states. We don't really verify the whole thing, by the way. But it's been a long time since we actually executed C programs in a computer, right? The compiler is generating basic blocks that average 6 instructions. We put in an instruction window of 800 instructions. We then go find out many, many parallel dependency graphs and execute those in parallel. And we're working on a generation that's significantly bigger than this and closer to the linear curve on performance, right? This is a really big mindset change. So, I'm going to finish up here in a few minutes. So, why do we make new computers, right? This is just data from the web somewhere. Like if you just look at the total numbers, the IPC went way up, the frequency 5 megahertz, we're shipping now 4.2 gigahertz Ice Lakes. Performance 14,000x. Like these are huge scaling numbers. And lots of people think, well, we're hitting some kind of limit. I really doubt it. We have a roadmap to 50x more performance, 50x more transistors, and huge steps to make on every single piece of the stack, right? And remember, computers are built by large numbers of people, but and actually many, many small teams, right? Better prediction, better instruction set architecture, better optimization, better CAD tools, better libraries, the number of different places that we're doing innovation is really, really high. Right? It's not one thing. We call it this Raja's law because Raja was the first one who showed me this graph, but I think it's an interesting phenomena, right? We had single core, single threaded computing, then it went up and kind of plateaued a little bit, and then we went to multi-threading, right? And then we went to GPU computing, and now we're working on AI computing, and we're working on essentially computers that compute across very large, very sparse data sets with very high computational intensity. And this is one place where Moore's law is enabling the architects to have a field day, right? And you can see when the idea sets are powerful. So when we first built parallel computers, lots of people thought, well, we'll make a parallelizing compiler, we'll take your C program, and the parallelizing compiler will make it work. And basically, I saw the first one of those in 1985. It didn't work at all, right? And parallelizing code was something that only a small number of people can do. And I still remember when Google built massive data centers with low-cost servers. They built a Google file system anybody could use. They used MapReduce and a bunch of tools where they got amazing scaling. Right. Now you could say it's not efficient. They could get 10,000 cores and go 1,000 times as fast. But 1,000 times as fast is really good, right? So there's a real creative tension on that. The GPU computing guys, man, they started trying to do computing on GPUs when they didn't even get the right answer. They didn't have any tools. People remember trying to write, OpenGL programs to get shaders to do what you wanted. But they co-evolved the software stack and the computing stack and the math engines underneath, and they started doing a credible job of computing. And now we're starting to do the same thing for AI. It's super interesting, and there's so far to go. So and this is what Roger said specifically, it's very hard to get software communities to move for 20% or 50% or even 2x. But for 10x computing, it enables a whole different genre of computing types. So the architecture challenge is to take all the transistors that we're building, build the architectures that let us solve problems, that kind of work your way up the stack. It's a super interesting problem. And we're literally in this transition. There was 100 million devices, then 1 billion devices. We're going into a world of 10 billion smart devices, and that curve, I believe, is not stopping. Now, we'll see how diverse they are. Cloud computing, mobile computing, personal computing, image processors, number of smart devices running all around is really incredible. So the opportunities for people, and in college today, looking at all kinds of different applications, it's really phenomenal and will continue to grow. I want to end on this thing and we'll take some questions. Richard Feynman famously said, there's a lot of room at the bottom, right? Our current transistors are 1,000 by 1,000 by 1,000. If we can get that to 10 by 10 by 10, that's 1,000,000x scaling. The kind of computer we build out of that, I don't even know if we know how to imagine that yet, right? It's going to be so many transitions over the next 10, 20 years. So I believe Moore's law is not dead. I hope I convince somebody. But more deeply, if your idea set says this is going to keep going and there's a whole bunch of challenges, then I think we'll rise to the challenge. And I've seen that over and over. If you think it's running out of gas, it will. If you think it's not going to. And there's many people in the industry working on this. We have so many people told me, well, computer architecture can't move any further. Really? How many times has it changed over the last 30 years? Like over and over and over. The hardware-software contract is really interesting. We've definitely found out that a more open source world is really interesting because when everybody participates, you gather that together. We saw that first in open source software. Amazingly, we're seeing it in security today. If you think security is keeping something secret and the secret gets out, then you're dead, right? If you think security is getting the best people to look at your stuff and investigate and collaborate with you, you have a plan for security. We see this in software, and the co-optimization of software architecture and actual chips we build is going to keep going. All right, with that, any questions? Thank you.
All right, great. So I know we have a lot of questions, so I'm gonna. Does this work? Do we know?
Well, if it doesn't work, I can always.
This does work. Oh, okay. We get to be interactive. Okay, so this is your question box. You're then responsible. We will pass it to the next person. We'll start here in the front, but it's going to work its way back.
Thanks for your talk. You gave a lot of hope for conventional architecture, but you just built a neural net accelerator at Tesla. Where does that fit in the computing landscape going forward? Is that going to revolutionize things? Is that a niche product? Or?
Yeah, I have a mixed feeling about it. So if people look at the human brain, there's the motor cortex and the reptile cortex and the lower primate, there's a diversity of thinking in our own brains, right? So I think computers will have diverse programming. I'm more interested in, I think, long run. Like right now, the AI world is changing very fast, right? So there's a lot of AI accelerators which are pretty bespoke to a narrow set of problems. And then there's things that are much more programmable. I like those. The widget we built at Tesla was super interesting because it runs the output of Cafe, right? That's a very programmable inference framework. And we can also port other things to that. And it had some very interesting phenomena. It's like, it's not hard to move the data around because the on-chip SRAMs hold the data, and it's not hard to run the instructions because it runs Cafe instructions. So that was an interesting accelerator experiment. And it let us go from standing start to driving a car in 18 months, right? Without the 6 years of software development, right? So the world's interesting right now. We're putting AI acceleration instructions in CPUs. The GPU guys are getting better at making them programmable, right? And then there's the bespoke accelerator kinds of things have a place. We saw it stabilize in like video encoding. And this was Roger's point. There's encoders and decoders, and you can get hardware for both on H.264. But on the cloud, the arms race is on the encoder, right? They're all software encoders. Because if you can tweak a little bit of compression with a new encoder, right, you can save a lot of bandwidth on the internet. But everybody's phone runs a hardware decoder. Like the decoder is the fixed target. And it could be AI is the same way. Training is a monster that's going to be evolving, and inference is a more simplified thing, but it's still pretty open-ended. And I think the experimental world is the right answer.
Well, if I could just sharpen up that question. So imagine the pie chart with all the silicon coming off fabs in 5 years. In that pie chart, how much of that silicon is CPU, how much of it is transistors devoted to GPU, and how much of it is neural net accelerator, like Mac
The
array?
software guys move slower than you think, and the AI is moving faster than you think. So today it's sort of 80 CPU, 20 GPU, 0 everything else. And if things move quickly, it'd be 1/3, 1/3, 1/3, but I don't think it'll move that fast, but I couldn't call it.
Okay, thank you.
So Moore's law is not dead. Dennard scaling's not dead, right? That's what you also said. So is the number of semiconductor companies shrinking?
Well, so a couple years ago, in the
No,
Valley.
the ones at the high end, right? That trying to push the state of the art.
No,
Is
here's
that shrinking?
here's the really wild thing. So the, you know how pendulums work, right? They swing back and forth, right? So, back in the late 90s, you couldn't kick over a rock without finding a chip startup, right? And everybody's doing ASICs, and then 5 years later, you couldn't get funding if you were doing hardware, because, quote, hardware doesn't make any money. And now there's 100 AI chip startups.
I was talking about semiconductor
Fabs, yeah, the big ones are Intel, TSMC, Samsung, behind GF, UMC, SMIC, and then there's like 5 more, so there's probably...
I thought some of them gave up on stuff leading edge.
GF famously said they're not doing 7. They have a huge business doing other technologies. So here's a really interesting thing. The business model of a semiconductor company is complicated. TSMC brags, it's on their website, they just keep building new fabs and they keep the old ones running. So at Tesla, we had a whole bunch of products in like 100 and something nanometer. So I would say today that there's a consolidation. Leading edge, there's 3. Next step, there's like 3 more. Next step, there's like 10 more. And then there's a whole bunch of bespoke technologies for like RF and special purpose power devices. And there's actually some new stuff there. So that's pretty good, and the investment is good. And the other, people always say, well, fabs are getting so expensive, you can't build a new fab. You know one thing the world doesn't have a shortage of? Money. Like, it's amazing how much we're spending on it. And EUV machines, when they came out, were like $400 million. They used to show, you go to a fab and they always have $1 billion row. So like there's 10 of these $100 million things, and we're replacing them with $300 million. It's gonna be $3 billion. The price of those things is crashing. So I don't think we're gonna run out of money. The worldwide appetite for square feet of semiconductors is still going up. All the big fabs are building more capacity. So we'll see what happens long run. And you can now get a startup funded building chips. And you can actually build chips in 18 months with 50 IPs, integrate them together, and power it on and drive a car. So I proved that.
Your abstract seemed to indicate you weren't that optimistic about voltage scaling and frequency scaling. But some of us think that there is, especially if you have an infinite amount of money, you can actually solve those problems too. What's your attitude about voltage scaling and frequency scaling?
So the roadmap I showed here didn't include much for voltage scaling or frequency scaling. We're working on it. I don't want to disclose what the frequency numbers are. They're pretty good. The voltage scale, so using silicon or germanium in fins and nanowires is moving the voltage a little. There's bigger developments to move voltage scaling further, and I'm totally interested in it. And it's definitely, like we're gonna see significant changes over the next 10 years, but I have nothing to talk about today. Next there was a couple.
More students back there. Here goes.
Whew.
That's off the deflection.
You're
Thanks.
doing a safe throw off the roof. It was a.
Thanks for the talk. I just want to know what's your view on trading off power area of frequency versus computation accuracy. Like, are you guys moving toward approximate computing, let's say a 12 transistor adder cell versus a 28 transistor? Because if the data is statistical, why should we have?
So there was people. Anybody know anything about AI in here? AI people. There's a couple years ago, there was a whole bunch of work about reduced precision, variable precision, and let's say fuzzy answers. And the problem is people are going to bigger and bigger data sets, and they're trying to get repeatability and convergence. Having fixed answers and data types really mattered. And most of the chips that the first spin was some reduced precision actually went into, and there's also some standards now. There's 16-bit floats, there's 2 formats of that, of course. People are working on some 8-bit stuff. You kind of, your intuition is, your brain seems to do a lot of computation, and it's pretty fuzzy. And it seems like a right answer, and we know that when you're training big data sets, you can sort of randomly nuke stuff without much loss of coherence. But the current thing is when you're in development mode, the repeatability is super important on the training side. And I know we did a lot of work. It's like, you get your new algorithms all work on 32-bit float, for Christ's sakes, because its stability is so high. And then as you refine it, you can drop down to 16-bit, and then the inference engines can pretty low. So there seems to be a lot of variability on that problem today. Directionally, it seems like fuzzy computes and approximate answers is the right thing, but to date it's been difficult to drive projects to completion that way.
Thanks.
There's someone behind you. Short throw. Hand off.
Nice. All right. What are your thoughts on FPGAs?
FPGAs, they're really cool. I built a lot of stuff using FPGAs. Generically, when you go from fixed accelerator to programmable thing, there's something like, let's say around, an average number of 10x perf per watt in performance. And then when you go to FPGAs, you might lose another 10x, right? Now, the good thing about FPGAs is you can build the algorithm you want, and that often works very well. And then there's a whole bunch of places in the industry where you want a specific chip and you don't have enough volume to justify the CapEx, the cost to build it, and FPGAs are great. So I've been intrigued that the FPGA companies were able to put multipliers and adders in FPGAs and then use that to get effective compute density out of them. But there's a pretty big spread on frequency and cost numbers. So the FPGA businesses are growing, but they're not like taking over computing, for example. So it's a little complicated. And the stuff you could do with FPGAs is great. Like we build FPGA models of everything we do now. Like they're the heart of all the emulation technology we have. And so FPGAs are super useful. If you go into network space and you pull out, there's FPGAs all over everything because there's lots of special purpose low volume devices that FPGAs are great at. So I'm a fan, I've used them a lot, but I'm not sure they're part of, as soon as the part of computing gets really big, building the purpose-built accelerator or the right extension for a programmable computer seems to win. There's a question behind you?
Well, it's interesting to see that you, on the graph for where we are going in terms of architecture from single core to multi-core. And it seems that for the next 20 years, AI will be a focus. And are you imagining that AI will be built into the Intel chip at the same level of branch predictor, instruction fetcher, or is a different abstraction?
I didn't quite understand your question.
So, how do you think the AI components for the chipset will be integrated with the existing instruction executor?
That's a really big question, and Intel just recently introduced what's called CXL, which is basically a coherent memory port, because we think there's going to be standard computers that run lots of C programs and JavaScript and all kinds of stuff, and then there's stuff that works really well on the vector architectures that GPUs have, and then the AI chips to date tend to be dense computational things like convolution, matrix multiplies, something that can take tensors right out of TensorFlow and do the right operations on them. But the algorithms are going to want to talk to each other, and the customers are uncertain what to build. Like one reason GPUs haven't gone bigger in the data center is if the GPU workload is half of your workload and is 10% duty cycle wise, then standing up the GPU data center is super expensive, right? And what people want is how do we get CPU, GPU, AI acceleration in the same box where it's really flexible to move the data back and forth and do it. And they want to do it in a flexible way, so if they think, well, I need this much GPU and AI computing, but it turns out to be true, they don't want to be stuck with the wrong computer set. So, did I answer your question?
Do you foresee that, say, in the future, Intel CPU, it will have instruction specialized for convolution?
Yes. Yeah, so the short answer is there's a whole bunch of stuff where you have the code, it's pretty good, and some kind of data type acceleration really works. And we'll definitely do that. We're working on multiple projects there. There's other things where either I have the data set and the math intensity doesn't really care about the unpredictable C code, or the data set is so big and weird that having a CPU grovel through it's not the right answer, right? So AI has significant diversity on how you want to architect for that. And
my question, is Intel looking for new materials, especially in Richard Feynman quotes, you highlight 7 atoms?
yes.
So can you...
We had we made a funny slide, and then I saw TSMC cribbed it. We did a walk through the periodic table. So, it used to be silicon and aluminum and silicon oxide, and the number of materials used in chip fabrication just keeps going up. We use more and more atoms, and then in terms of, as you're alluding to, in terms of the actual device type, it's really interesting what's going to happen, but That's not my exact wheelhouse, but you want to answer that question? Carbon. We'll see what happens. Like the material science, we've just scratched the surface on material science. I mean, you get a couple atoms together and have them talk. Like, it's so unpredictable. Like, does everyone know how Schrodinger's equation works? Right? You can write it down, it's pretty simple. What have we solved? Hydrogen? Sad story. Like, material science is amazing. And,
You got a long throw to the front here. Okay, it's going to go this way.
oh, look at that, a handoff,
All right.
relay, cooperation,
So
teamwork, yay.
I was interested in your comments about FPGAs because it's one thing that's missing from all your graphs and all your charts, all these big multipliers, but nowhere did you see anything about NRE, right? So non-recurring engineering, right? So the cost to develop a new design, that's probably going up pretty steep as well. You were a little, hesitant about FPGAs and really making
Well,
a big
I can
impact.
give you some
So
numbers.
what can you do? You got any other way to beat down the NRE so that small companies can, come up with new products quick?
So,
that,
so let me
based
just give
on
you
a
some
fancy
numbers.
chip?
On 130 nanometers, you can build a sophisticated device for about $1 to $2 million. Is that right? On 28 nanometer, I built multiple parts for $10 million. 14 nanometer, 40, right? An advanced process node, like depends on how you allocate the cost, who the hell knows? Hundreds of million if you take the process for granted, billions if you need to build the cost. So the diversity in cost, let's imagine to do a new product ranges from $2 million to $2 billion. It's fairly diverse, right? Now FPGAs are really interesting because if it's a small number of parts, even at $2 million, it takes a lot of parts to amortize that, right? And if you're doing experiments in a research lab and you don't care about the current frequency, but you really want to do architecture experiments, modern FPGAs are great. The tools work way more than they used to be. You can get a stack of HAPS boards with a boatload of FPGAs on each one and standard interfaces. And I'm sure that some of the students here have built some really cool computers using the FPGAs and working memory controllers and Ethernet NICs and embedded CPUs so you can do what you want. So I'm a huge fan of that. But I would say just think 2 million to 2 billion is the range, depending on what you're paying for. Advanced technology, 16 FinFET, 25 to 45. You start going into 7 nanometer, you're starting to look at, 5 to 10 million for mask costs alone, right? But everybody says, well, it's just going to explode and run out of control, but then the mask costs on the trailing nodes keep coming down. And like 16 FinFET, when it first came out, that was a $100 million minimum. And they're down under 40, and they're on their way to 20. So it keeps moving. And then you have to say, what do I need to make it a competitive product? If it's architectural innovation is 10x the other guy, then the 2x on the process isn't the thing. But if everybody is on the process, they have the equal architecture, then the process is the differentiator. And that stuff is pretty stable.
You have the box. All right, I'm going to take the last question. Okay, let me take one more and then I want to ask. So, yeah, I want to give.
Yeah, hi. Great talk. So one thing I was wondering is in that chart of processors you had, while compute seems to be scaling pretty fast still, the size of the register files and cache isn't really scaling as fast. So is that going to bottleneck things, and how might we mitigate that?
Yeah. So I mean, so there's a big step function. So the L1 caches are like 32 to 64K because they're trying to keep in a 4-cycle load-to-use pipeline. And to grow that, when you step off that one more cycle, you get 2% on the bigger cache and you lose 5 to 7% on the latency. So we build L1 caches, mid-level cache, last level cache. So the trade-off has been around the cache hierarchy. The instruction stream caches have gotten bigger faster. But that trade-off is out of a fairly sophisticated performance model environment. And then the other thing is we build more load store pipes right when you want to make the L1 caches bigger. Instead, you put more ports in them. So those modern caches have a lot of ports, like 5 or 6 or 8, read-write ports. And so we've sort of been spending the bits and the transistors and metal tracks on ports more than size. and then trying to compensate with big block moves out of the mid and left level cache. So, it's a cool question. There's one more back there.
Thanks. So this may be a slightly off-topic question, but Intel and IBM have both come up with quantum computers equipped with like 49 and 51 qubits. And so is there a competition between the two technologies? Because they're two very different types of processing. So is there like a competition between which one is going to prevail? If so, which do you think is going to win?
I literally have no opinion. I've been watching quantum computing for years, and I had a friend who was working on it for a couple of years, and he said, "I'm not sure it's not a fraud." Because we haven't really gotten results out of it. And I'm curious because, you know, the physics says a whole bunch of interesting things is happening, but we haven't really gotten the results that we expect. But they are making progress, and so I would have to direct you to the current papers more for answers to that. Okay. Great. Thanks, everybody.
All right. Actually, I had one more question, which was a little bit of you've had this amazing career of different places where you've worked. I'm wondering, you have an audience of certainly the next generation of practitioners in this space. So you have advice to students, or what do you wish that someone had told you when you were in this seat? What's your kind of messaging?
Well, first, if they told me something, I wouldn't have listened. So I'm not really, when I was in college, I was a double E, and then a senior year, we had a 2-inch wafer fab, and my advisor ran it, so I worked on semiconductor physics, so I thought that was super cool. And then my first job I took in Florida because I want to live next to the beach and surf. And surfing was shitty, and the company was horrible. But I learned, they threw me in the lab, and I fixed stuff, and I got to be a scope jockey, and I could fix bloody anything in the lab. And it was like one of those worst 2 years of your life and best 2 years of experience. And then somebody told me I should work for Digital Equipment. So I went, back then his newspaper, EE Times, and I found an advertisement, a recruiting ad for Digital Equipment. And I read the VAX 11780 manual and the 1170 manual on the plane. And I talked to the chief architect, Bob Stewart, of the VAX 11780, which is a very famous computer. And he said, "All right, so why are we here?" And I said, "I have a lot of questions for you." And it turns out he thought I was a complete goof, but he thought it'd be funny to have me work for him. My thing is I like to throw myself into stuff and learn what I can, and then make sure that you're working with people who are excited. Like I worked at Harris as the Florida company, and at lunch all people did was complain. And then I was at Digital in the first 8 years there. A friend of mine's wife said, "What do they put in the water? All you guys do is work, and when you got drinking, you talk about work." And it was super fun. And way back when I gave a talk, a microprocessor forum on the VAX 8800, which was my first computer. I worked on, it was kind of weird, I was a junior person and my boss quit and then his boss quit, and we got all done. I was the chief architect of the cache system. And there was no poison involved. And I gave a talk on it, and I was a nervous wreck, and after me was Marty Hopkins, who was a fellow at IBM, who's a great guy. And then we were all standing around, there was like a little chat, and he said, because back then you went to a computer conference, I remember the RISC wars, you'd say this and they'd say that, and everybody was all, and he said, we're so passionate about this because it's a great endeavor. And I thought that. It was a perfect way to say it. There's so many technologies involved, it's so transformative to society. So many good things have happened, some bad things, obviously. So find some smart people that are excited about it. If everybody's all bummed out and ragging on the company, go somewhere else, right? Or be a change agent. I worked at AMD after they'd fired half the people. It was not a happy place, right? But my conviction was if we go do the right thing, design the right thing, put our energy into it, we'll do something cool. Now it's a happy place. So Intel is a way wilder place because we had record revenue. We have some stuff that's great, some stuff that's not so good. Super fun for me because I like to think about those problems. But
Well, great. Thank you for bringing that energy here, and thanks, Jim, for giving a great talk. He's going to stick around a little bit. If you want to interact with him, please come up. Thank you again, Jim.
Great.